Module 2, Lecture B, Functions and Modules. By the end of this lecture, you will be able to define functions that accept electrical parameters and return calculated engineering results. Use parameters, return values, and default arguments to make calculation functions flexible, and organize related functions into simple modules for reuse across engineering scripts. Function basics. Define functions. In engineering, a function is a reusable tool for performing a specific calculation. For example, in electrical systems, a function can use current and resistance to calculate power dissipation. Defining the calculation once makes it easier to reuse across components or circuits, while keeping the behavior consistent and reliable. Using functions in a script makes complex electrical analysis easier to read and maintain. Well-named functions keep calculations separate from tasks like reading sensors or checking limits, so the main script shows the overall purpose more clearly. They also make teamwork easier, because one person can create a reusable calculation that others can apply in reports or testing. A well-designed function should do one clear task, use the inputs it needs, and return a result that other work can build on. This matters in engineering because calculations often feed into later decisions, such as checking component safety or cable suitability. Organizing calculations into functions makes them easier to test, understand, reuse, and adjust as design conditions change. Python code. Define functions. Functions group repeated engineering calculations into reusable pieces. Parameters bring values into a function, and return values send the result back. This function calculates the power dissipated by a resistor using the current in amperes and the resistance in ohms. It squares the current, multiplies it by the resistance, and returns the resulting power in watts for use elsewhere in the program. The voltage drop function calculates the voltage across a resistor using the current in amperes and the resistance in ohms. It multiplies these two values according to Ohm's law and returns the resulting voltage drop for use elsewhere in the program. Set the circuit's example values as a load current of 2 amperes, a resistor value of 8 ohms, and a wire resistance of 0.35 ohms. These inputs describe the current path and resistances, and they will support later calculations of quantities such as power and voltage drop. The calculations find 2 key circuit values. First, the power in the resistor is computed from the load current and resistance, using current squared times resistance. Then, the wire voltage drop is found from the load current and wire resistance, using current times resistance. Together, these results help describe how the circuit components behave electrically. The output begins with a brief introduction to the electrical calculation examples. It then shows the resistor power and wire voltage drop, each formatted to 2 decimal places for clarity. The example ends by noting that the defined functions can be reused for similar calculations. The script defines 2 reusable functions for simple electrical calculations. One finds resistor power by multiplying resistance by current squared, and the other finds wire voltage drop using current times resistance. With a current of 2 amperes, it calculates 32 watts for an 8 ohm resistor and a 0.7 volt drop across a 0.35 ohm wire. The printed results show how the functions support repeated engineering calculations. Current parameter. Using current as an input to a function lets engineers calculate important circuit behavior, such as voltage drop and power use, from the charge flow in a specific device. This makes the same calculation reusable for different circuits, including sensors and motor controllers. It is an efficient programming approach because one procedure can handle many current values without repeating manual work. Using current as an explicit function input makes engineering calculations clearer and more reliable. Current values can come from measurements or simulations and may change with operating conditions, such as startup versus steady-state behavior. Requiring the user to provide this value avoids hidden assumptions and makes scripts easier to review, reuse, and apply correctly. Calculation functions should define and use the current parameter clearly, with a name and documentation that specify its unit, such as amperes or milliamperes. This prevents scale mistakes that can cause major errors in power and energy results. Treating current as a parameter also makes the function useful across different circuit sizes, turning repeated calculations into reliable engineering tools. Python code. Current parameter. Functions can take current as an input, making electrical calculations clearer and easier to reuse. When doing this, it is important to handle current units carefully to keep the results accurate. The power watts function calculates electrical power from voltage and current. It takes voltage in volts and current in amperes, multiplies them, and returns the result in watts. This makes it easy to find power when both standard measurements are known. A helper function accepts current in milliamps, converts it to amps by dividing by 1000, and then passes that value with the voltage to the power calculation function. This keeps the main power logic reusable while allowing inputs in a different current unit. The example shows two ways to calculate electrical power, depending on the current unit. For a sensor, the milliamps function converts 40 milliamps to amps before using 5 volts to find the power. For a motor, the amps function uses 24 volts and 1.8 amps directly. Together, these cases show how both functions compute power correctly from voltage and current. The program reports that the sensor uses 40 milliamps at 5 volts, then displays its calculated power. The power value is rounded to 3 decimal places, so the result is concise, readable, and professionally presented. The code describes a motor drawing 1.8 amperes at 24 volts, then uses the power function to calculate its power. The result is rounded to 2 decimal places, showing how the function can handle a larger current value and present a clear output. This example shows why correct units matter when calculating power. A power calculation using 5 volts and a current entered as 40 amperes gives a much larger result than intended because the current was actually meant to be 40 milliamps. The printed output highlights this mistake and shows how confusing milliamps with amperes can make the power value incorrect. This script shows how to calculate electrical power while handling current units correctly. It multiplies voltage by current in amperes and converts milliamps to amperes when needed. For example, 5 volts and 40 milliamps gives 0.2 watts, while 24 volts and 1.8 amperes gives 43.2 watts. It also shows that treating 40 milliamps as 40 amperes gives a wrong result of 200 watts, highlighting why unit conversion matters. Resistance parameter. Resistance measures how strongly a component opposes electric current. When a function uses resistance as an input, it can calculate related values such as voltage or power for different components, including resistors, motors, or cables. This makes the function reusable and efficient across changing physical situations. A well-designed calculation function treats resistance as a precise engineering value with clear units and meaning. Its physical role may differ, such as a sensor component, cable resistance, or heating load, but the calculation can use it in the same structured way. This separation between the general calculation and the specific input makes the function more flexible and useful in engineering. Including resistance as an input makes calculations clearer and more reliable, because resistance can change with temperature, aging, or measurement conditions. A lab calculation may use a nominal value, while an industrial analysis may need a measured or corrected value. This lets the function stay general, while the engineer chooses the resistance value that best fits the situation. Python code. Resistance parameter. Functions help make electrical calculations reusable. Resistance parameters describe how much a circuit opposes current, and return values keep the calculated results available for later use. The voltage drop function takes current in amperes and resistance in ohms, then calculates the voltage drop by multiplying them. It returns this voltage in volts, so the result can be used or displayed elsewhere. The power loss function calculates how much power a resistor dissipates. It uses the resistance and current, with a default current of 2 amperes if none is provided. The power is found by multiplying the resistance by the current squared, and the function returns that value in watts. The setup uses a catalog resistance of 10 ohms, a measured resistance of 10.8 ohms, and a load current of 1.5 amperes. These values allow comparison between the standard and actual resistance, and support later calculations such as voltage drop or power loss. We compare voltage drop using the catalog resistance and the measured resistance to see how the actual component affects circuit voltage. Then, we use the measured resistance with a default current of 2 amperes to estimate power loss, showing how much energy is dissipated as heat due to resistance. The script prints a short results summary for the resistance calculations. It reports the voltage drop using both the catalog resistance and the measured resistance, with each value rounded to 2 decimal places. It also shows the power loss for the default current, giving a clear final overview of the key engineering results. The script uses 2 helper functions to calculate basic electrical values. One finds voltage drop by multiplying current by resistance, and the other finds power loss from current squared times resistance, using 2 amperes by default. It compares voltage drop for catalog and measured resistance values, then reports the power loss for the measured resistance, with results printed to 2 decimal places. Reusable calculation functions. Voltage parameter. Using voltage as an input makes a calculation function flexible across different electrical situations. The same function can evaluate systems, such as a lab supply or solar panel, without being rewritten. Changing the voltage lets technicians compare component behavior under different conditions while keeping the calculation logic separate from the data. Using voltage as an input to a function makes the operating condition clear instead of assumed. This helps students and engineers compare designs more accurately because results are tied to the specified voltage. By adjusting that input, they can evaluate performance under different power sources or circuit conditions with better context. A voltage input should be named and used according to its real physical role in the circuit. The chosen value must fit the calculation, such as a source voltage, voltage drop, or node voltage, because the wrong choice can give mathematically valid but physically misleading results. Making voltage an explicit input encourages careful engineering judgment and helps the function produce results that make sense in the real electrical system. Python code. Voltage parameter. Using voltage parameters makes electrical calculation functions more reusable and clearer. By exposing assumptions and using default arguments, the same function can support flexible comparisons without unnecessary repetition. The calculate current function is a reusable way to find electrical current from voltage and resistance, with resistance defaulting to 1000 ohms if not provided. It first checks that resistance is positive, raising an error if the value is 0 or negative. Then it applies Ohm's law by dividing voltage by resistance and returns the resulting current. The function uses Ohm's law to calculate current by dividing voltage by resistance. It then returns the current in amperes, so the result can be reused with different voltage and resistance values elsewhere in the program. We set 3 voltage levels to compare how they affect current in a circuit with fixed resistance. 5 volts for a bench supply, 3.7 volts for a lithium-ion battery, and 12 volts for a standard adapter. These values will be used to calculate and compare the resulting current at each voltage. The same current calculation is applied to a 5-volt supply, a 3.7-volt battery, and a 12-volt adapter, each using the default resistance of 1000 ohms. This shows how a default resistance value lets the function be reused easily for different voltage sources, while producing the corresponding current in each case. The example prints a header, then shows calculated current values for 5 volts, 3.7 volts, and 12 volts, each rounded to 4 decimal places. This consistent formatting makes the results easy to compare and demonstrates how the same function can reuse a voltage input while keeping resistance constant. We calculate current using 3.3 volts and a resistance of 2200 ohms, replacing the default resistance value. This shows how changing resistance affects the current through the sensor. The result is then printed to 4 decimal places for a clear reading. This script uses a reusable current calculation function that takes voltage and resistance as inputs, with resistance defaulting to 1000 ohms unless a different value is provided. It calculates and prints current values for 5 volts, 3.7 volts, and 12 volts using the default resistance, then shows how to override the default by using 3.3 volts with 2200 ohms. The example highlights how one function can flexibly compare current for different voltage and resistance values. Default parameters. Default parameters make calculation functions easier to use by supplying sensible values when inputs are not specified. In engineering, where many problems reuse common conditions, these defaults reduce repetitive input while still allowing changes for special cases. This makes repeated calculations clearer, faster, and more efficient. A good default parameter makes an engineering assumption explicit, showing what conditions a calculation expects unless the user says otherwise. In resistor power rating work, a default safety margin can support standard estimates, while still allowing changes for tougher settings such as automotive or outdoor use. Defaults help keep typical calculations clear and consistent, but they do not replace engineering judgment. Default parameters make calculation functions easier to read, test, and maintain by separating required inputs from optional settings. They let common assumptions stay built in, while allowing changes when needed, such as for tolerance or temperature. This keeps electrical calculation functions simple for basic exercises, but flexible enough for more advanced design work. Python code default parameters. Default parameters make repeated engineering calculations easier by providing standard assumptions automatically. In this example, they help estimate resistor power ratings, while still allowing callers to override the usual design assumptions when needed. The required resistor power function estimates both normal and safe power requirements for a resistor. It uses the voltage and resistance to calculate actual power. then multiplies that value by a safety factor, which defaults to 2. The function returns both values so the user can compare the basic power dissipation with the recommended rated power. The function returns both actual power and rated power. Actual power is found from voltage squared divided by resistance, while rated power adjusts that result by applying the safety factor. This gives both the raw calculation and the safer rated value for later use or display. We use the resistor power calculation function with 12 volts and 100 ohms, relying on its default safety factor. It calculates the actual power from the voltage and resistance, then doubles it to find the rated power. Both results are returned and stored for later use. The resistor power calculation is run again using a harsher safety factor of 3 instead of the default value of 2. The function returns the actual power and the required rated power, allowing the normal and harsher operating conditions to be compared. The output first identifies that the results use the default safety factor. It then shows the calculated resistor power in watts, rounded to 2 decimal places. Finally, it presents the recommended power rating, also rounded to 2 decimal places, which includes the safety factor for safe operation. The output compares power requirements using overridden default settings for a harsher environment. It labels the scenario, then prints the calculated actual power and the recommended power rating, each rounded to 2 decimal places in watts. This makes it easy to see how more demanding conditions affect the required power. The script estimates the required resistor power rating by calculating actual power from voltage and resistance, then multiplying it by a safety factor. With a 12-volt source and a 100-ohm resistor, the actual power is 1.44 watts. Using the default safety factor of 2 gives a recommended rating of 2.88 watts, while a safety factor of 3 raises it to 4.32 watts. This shows how harsher conditions require a higher recommended power rating. Resistance parameter. Making resistance an input to a calculation function makes the function flexible for different components and real conditions. Instead of being tied to one fixed resistor, it can adapt when parts are changed or extra resistance appears, such as in cables. This turns the function into a reusable tool for many electrical scenarios. Using resistance as a function input makes electrical calculations clearer and more flexible. The function can combine resistance with values such as voltage or power and return the needed result without depending on where the resistance came from. This keeps the same function useful across applications, such as estimating voltage loss or interpreting sensor signals. Default resistance values can make calculation functions faster and easier to reuse when one value is commonly used. However, defaults should be chosen carefully so they do not hide important circuit assumptions or cause errors in different situations. Clear naming and documentation help users know what the resistance means and when to change it. Python code, resistance parameter. Functions help reuse electrical calculation logic instead of rewriting it each time. Using resistance parameters makes formulas more flexible, while default arguments support common engineering assumptions. A current calculation function uses Ohm's law by taking a voltage and a resistance, with the resistance defaulting to 1000 ohms. It first checks that the resistance is positive and raises an error if it is not. If the input is valid, it returns the current in amps by dividing the voltage by the resistance. The function uses Ohm's law to calculate current by dividing voltage by resistance. It then returns the resulting current in amperes. This function calculates the voltage drop across a wire using the current in amps and the resistance in ohms. it provides a default resistance of 0.25 ohms for typical wiring cases. Before calculating, it checks that the resistance is not negative and raises an error if the value is invalid. The function finds the voltage drop across a resistor by multiplying the current by the resistance. It returns the result in volts, applying Ohm's law to relate voltage, current, and resistance. A collection of component design cases is created, so the program can process several examples in the same way. Each case stores a name, a voltage, and a resistance, including examples for an LED test load, a heater element, and a sensor input. This structure makes it easy to loop through the cases later for calculations or comparisons. This example shows how to reuse a current calculation function with different resistance values. After printing a short header, the program goes through several cases, each with a component name, voltage, and resistance. For each one, it passes the voltage and resistance into the function to calculate the current in amps. The code converts current from amps to milliamps by multiplying by 1,000, which makes small electronics currents easier to read. It then prints each component's name with its converted current, rounded to 2 decimal places, so the results are clear and easy to compare. The current is calculated from the voltage using a default resistance of 1,000 ohms, a typical test load. The result is in amperes, then converted to milliamps by multiplying by 1,000. The final value is printed in milliamps and rounded to 2 decimal places for clarity. To compare voltage drops in short and long wires, use the same current of 2 amps with different resistances. The short wire has a resistance of 0.08 ohms, while the long wire has 0.4 ohms. The higher resistance in the longer wire produces a larger voltage drop, showing how wire length and resistance affect voltage loss. The program prints the calculated voltage drop for both a short cable and a long cable, formatting each value to 2 decimal places. Comparing these results shows how increasing cable length increases voltage loss, which is important when designing efficient electrical systems. This script uses Ohm's law to calculate current and voltage drop in simple electrical examples. It computes current from voltage and resistance for cases like an LED load, heater element, sensor input, and a default 5-volt source with 1,000 ohms. It also compares voltage drop in short and long cables, showing how higher resistance increases the drop. Overall, the examples connect basic electrical calculations to practical component and wiring design. Simple Python modules. Module basics. A Python module is a reusable toolkit for storing functions and constants. In engineering, this helps keep common calculations, such as power computations or unit conversions, organized and easy to use across programs. By putting trusted code in a module, you avoid rewriting or copying past work and can focus more efficiently on new tasks. A well-structured module keeps related tools together for a clear purpose, making code easier to understand and reuse. In electrical engineering, modules can separate tasks such as calculations, conversions, or data processing, so the main script stays focused and uncluttered. Keeping reusable functions in one place also improves maintenance, because updates are made once and applied consistently across scripts. Modules support professional computational engineering by making functions clear, reliable, and reusable. Well-designed modules have defined inputs, outputs, and roles, which reduces errors and helps other scripts depend on them safely. This practice is useful for individual work and becomes essential in team projects, where shared, tested routines keep analyses consistent. In this way, modules turn small scripts into dependable tools for repeated engineering work. Python code, module basics. Modules let you store reusable engineering calculations so they can be used in other scripts. In this example, a small module is created and another script imports its tools. We import a utility from Python's import library and give it a simpler name for convenience. This tool lets us load modules dynamically from a file path, which is useful for temporary or reusable code. It supports modular scripts without permanently changing the working environment. We import Python's standard tools for temporary files under a convenient alias. This lets us create and manage temporary files for module code without changing the permanent file system. A string constant is defined to represent the unit ohm for electrical resistance. Using a constant keeps the wording consistent across the code and avoids repeating the same text in multiple places, making future updates easier. The current amps function calculates electric current in amperes using voltage and resistance as inputs. It applies Ohm's law by dividing voltage by resistance, giving the current flowing through a circuit. The power watts function calculates electrical power from voltage and current. It takes voltage in volts and current in amps, multiplies them, and returns the power in watts. The series resistance function calculates the total resistance of resistors connected in series. It accepts any number of resistance values in ohms, adds them together, and returns the total resistance for the circuit. We create a temporary Python file to hold module code, opening it in write mode so the code can be saved. The file is kept after closing, which makes it available to import later. This lets the script dynamically create and use a module. The module code is written to a temporary file, saving its functions and constants as text. The file is then closed to ensure the data is saved correctly and the module is ready to be imported and used by the main script. Before importing the module, we create an import specification using the module loader's file location feature. This specification names the module Circuit Tools and points to the temporary file containing its code. It serves as the blueprint for loading the module into the script. First, a module object is created from the existing specification, which prepares the module in memory. Then the module's code is executed inside that object, making its functions and definitions available. This effectively imports the module's functionality so the main script can use it. Set the voltage to 12 volts, then find the total resistance of the series circuit using the series resistance function with resistors of 100, 220, and 330 ohms. Finally, use the current amps function to divide the voltage by that total resistance and calculate the circuit current in amps. Use the power watts function from the Circuit Tools module to calculate power by multiplying voltage in volts by current in amps. You can also access the module's special name attribute to get the module name as a string, which is useful for printing or logging identification information. The output first confirms that the module loaded by printing its name. It then shows the circuit's key results: total series resistance to 1 decimal place, current to 4 decimal places, and power to 4 decimal places. Together, these values give a quick summary of the circuit's main electrical measurements. This script shows how to create a temporary Python module and use it for basic electrical calculations. The module provides functions for current, power, and series resistance. Then the main script imports it to find total resistance, current from a 12-volt source, and power consumed. It also prints the module name and the calculated values, demonstrating dynamic module creation and use in Python. Grouping reusable functions. Creating a Python module lets engineers collect reusable functions into one reliable toolkit. For tasks like unit conversions and power estimates, this reduces repetition and helps keep results consistent across scripts. By importing only the needed functions, engineers can work more efficiently and focus on solving the main problem. Group related engineering functions into clear purpose-based modules to make scripts easier to read, extend, and revisit later. Modules should reflect how engineers think about tasks, such as separating circuit calculations from measurements or unit conversions, without being too broad or too narrow. This organization improves naming, documentation, and the ability to quickly find related calculations. Reusable modules help larger engineering projects stay organized and consistent. They let team members develop separate parts, such as battery analysis or voltage processing, while keeping the overall workflow connected. This reduces duplicated work and makes updates easier, because improving one shared module can benefit every script that depends on it. Python code. Grouping reusable functions. Grouping related functions into a module makes them reusable across engineering scripts. In this example, one small module file is created, and a separate script imports and uses its functions. The code imports the path class from Python's pathlib module to work with file system paths in a clear, object-oriented way. Here, it is used to create and write a small module file containing reusable functions for electrical calculations. This module defines a reusable function that calculates resistance from voltage and current. It first checks whether the current is 0 and raises an error if so, preventing division by 0. Otherwise, it returns the resistance by dividing voltage by current. The DC power function calculates direct current power by multiplying voltage by current. It takes voltage and current as inputs and returns the power, a basic measure used in electrical engineering to describe how much power a circuit uses or delivers. The voltage drop function calculates the voltage lost across a cable. It uses the current, resistance, and a cable length, with the length defaulting to 1 meter if not provided. The result is the current multiplied by the resistance and the length. This creates a small Python module file in the current directory using a path handling tool from the standard library. It writes the stored module content into that file, making the defined functions available for reuse in other scripts. This code imports selected functions from a Circuit Tools module, so the script can use them directly. These include functions for calculating direct current power, resistance from voltage and current, and voltage drop. Importing them this way supports modular, reusable, and easier to maintain code. This code sets up a simple metric circuit example with a voltage of 12 volts, a current of 2 amperes, and a cable length of 3 meters. These values are used to calculate key electrical properties such as resistance, power, and voltage drop. The circuit calculations find 3 key values: the load resistance from voltage divided by current, the load power from voltage multiplied by current, and the cable voltage drop from current, cable resistance, and length. Together, these show how much the load resists, how much power it uses, and how much voltage is lost in the cable. The output begins by identifying the module file, circuittools.py. so the source of the reusable functions is clear. It then reports the calculated load resistance in ohms, load power in watts, and cable voltage drop in volts, each rounded to 2 decimal places for a concise summary of the results. This example shows how to build a reusable Python module for basic electrical calculations, including resistance, direct current power, and cable voltage drop. The functions are imported and used on a simple 12-volt, 2-amp circuit with a 3-meter cable. The calculation gives a load resistance of 6 ohms, load power of 24 watts, and a voltage drop of 0.48 volts, demonstrating how modules make engineering calculations easier to reuse. Testing module functions. Testing functions in a Python module helps ensure engineering scripts behave reliably across different inputs. By checking key calculations, such as power or resistance conversions, you can catch errors early and build confidence that the module will support future projects and collaboration. Test your module functions first with simple cases where the correct result is easy to predict, such as familiar class examples or verified datasheet values. Then check boundary and unusual inputs, since engineering data can include values like zero current or extreme tolerances. Testing ordinary, edge, and unrealistic cases helps ensure your functions behave predictably and handle unexpected inputs gracefully. Testing helps keep a module reliable as it changes. When functions are revised or expanded, tests catch problems that could break scripts that depend on them. By checking functions individually before using them in larger projects, engineers support quality assurance, safety, and dependable results. Python code, testing module functions. Testing verifies that a reusable electrical module works as intended by comparing its outputs with expected results. Simple checks confirm normal behavior, while edge cases help uncover hidden calculation errors. To create a temporary module, we import 3 key tools. The Import Utilities module lets us load a module from a file path. The Path library helps manage file system paths. And the Temporary File module lets us safely create temporary files or directories for testing without changing the main file system. A temporary module is defined to test a direct current power function in a controlled way. The function takes voltage and current as inputs and returns their product, which gives the electrical power in watts. The series resistance function accepts any number of resistor values and adds them together to find the total resistance. This gives the equivalent resistance for a series circuit, where resistors are connected end-to-end and their resistances combine directly. The voltage drop function calculates the voltage lost across a conductor. It uses the current, resistance, and an optional lead length, which defaults to 1 meter. The result is current times resistance times lead length, giving the voltage drop for that conductor length. A temporary directory is created to safely store module code in an isolated location. A Python file for the module is then placed in that directory, and the prepared module text is written into it. This saves the code as a real file, so it can be imported and run later. To load a custom module, ImportLib is used to create a module specification with the module name and file location. That specification acts as the loading plan, which is then used to create the module object in memory. Finally, the loader executes the module code, making its functions available to the script. The test cases are stored as tuples that include a clear test name, the actual function result, and the expected result. They check key circuit tool functions, including direct current power, series resistance, and voltage drop, using typical values and an edge case with zero current. Comparing the actual and expected results helps confirm that the module behaves correctly. The code counts how many test cases pass by checking each actual result against its expected value. It allows for tiny floating point differences by comparing the absolute difference to a very small tolerance. For each test, it updates the pass count when the result is acceptable and prints the test name, expected value, actual value, and whether it passed. The code prints a brief test summary by inserting the number of past tests and the total tests into the output. This gives a quick check of how many module tests succeeded, helping confirm the functions are reliable before reuse. This script creates and tests a temporary Python module for basic electrical calculations. It checks direct current power, series resistance, voltage drop, and a zero current power case against expected results. Each test reports whether it passes. Then the script summarizes the total successes. Overall, it verifies that the module works correctly for the selected scenarios. In this lecture, you learn to define functions that accept electrical parameters and return calculated engineering results. Use parameters, return values, and default arguments to make calculation functions flexible. And organize related functions into simple modules for reuse across engineering scripts. In the next module, Module 3, we will go over none.
Thank you for your attention. See you all in the next lecture.